Let us conclude by studying what are the expected value and the variance of a signal which is obtained from two other signals using an arithmetic operation. Let us begin with sum or subtraction. We know that the expected value of z, we have already proved this, is the sum or subtraction of the expected values of the signals from which it was built. This is not difficult to prove. We know that the expected value is the limit of the average. The limit as final time goes to infinity. Now, this integral here is a linear operator, and it is straightforward to show that each of these limits is, of course, the expected value of each of the two signals x and y. What if z is obtained from x and y not by adding or subtracting the signals, but by multiplying them? We remember that by definition, the cross-correlation coefficient of x and y is given by the cross-correlation of x and y minus the respective mean values or expected values divided by the standard deviations. Now, if we make tau equal to 0, we get the cross-correlation coefficient. Remember that without an argument, this is a scalar and this is the value for 0. We have here the cross-correlation of x and y for 0. These are, remember, the expected values. And here we have the standard deviations again. But this cross-correlation here is the expected value of the product of x and y for time instants that differ by 0. So this is any value t, this is the same value t. We want to find this expected value. So of course it's just a matter of solving this in order to this expected value. So in this case, it's not just a matter of multiplying the two expected values. There is an additional term here. Going back now to the case where z is equal to the sum or difference of x and y, we can also find the variance of z using two results. One is this, which we have just found about the expected value of the product of two signals. The other is the result according to which the expected value of the square of a signal is equal to the square of its expected value plus its variance. So if we want to know the expected value of z squared, where z is equal to x plus or minus y, we will end up with the expected value of x squared plus or minus 2xy plus y squared. And since the expected value is a linear operator, here we will apply this result. Here and here we will apply this one. Now it's a matter of rearranging terms. We know that the sum or difference of these two expected values is also the expected value of the corresponding sum or difference of these two variables. And this squared. Now, this sum or difference is z itself. But we know from this expression here that the expected value of z squared is equal to the square of the expected value of z, here it is, plus the corresponding variance. So this has got to be the variance of z.